Okay, in this video I want to talk about ideal gases and property changes of ideal gases. So look at ideal gas properties. With ideal gases, well, with properties in general, we said that one property, for instance the internal energy, is a function of some other two properties. Usually you'll see the internal energy written as a function of T and V. So a small change in T and a small change in V will give you a small change in U. du is equal to delta U, I should say delta U is equal to delta T, delta U, delta T, a constant V times a small change in T, plus delta U, delta V, a constant T, times a small change in V, delta V. Now, if you've had multivariable calculus, this is generally written as du is equal to partial of U, partial of T at constant V, dt, plus partial of U, partial of V at constant T, dV. Now, for ideal gases, it can be shown that du dV at constant T is equal to 0. 0 for an ideal gas. And so that reduces our problem to du for an ideal gas is equal to du dt at constant V times dt. Now this term here, the partial, which is also a slope, remember that's an infinitesimally small delta U over delta T. That's the slope, how much U, or the internal energy, changes with temperature. That's used so widely that we have a name for it. It's called CV. And CV is referred to as the constant volume heat capacity. So constant volume heat capacity. Constant V heat capacity. So that's referred to as CV, and so that we can say that for an ideal gas we have du is equal to CV dt. Now that makes our problem a bit simpler because we don't have to consider changes in volume, and now the internal energy change of an ideal gas is a function of only one property, T. Okay, now we'll talk about changes in enthalpy. dH is equal to, often written as a function dH of T and P. We'll take the two variables temperature and pressure, and that's dH dt at constant P times small change in T, dt, plus dH dP at constant T times a small change in pressure. And it can be shown, again for an ideal gas, that this dH dt dP goes to 0, ideal gases. And so for an ideal gas we have dH equals dH dt at constant P dt. And this value here, this slope in front of the dt, is so widely used, it's given a symbol C sub P. And C sub P is what we call the constant pressure heat capacity. Constant pressure heat capacity. and that's a function of the fluid. And so for an ideal gas, we can say dH, or function of the material, I should say, fluid or solid. dH is equal to Cp dt. So for an ideal gas, we can say the following things are true. du is equal to Cv dt, and dH is equal to Cp dt, and also, as we learned earlier, PV is equal to, of course, N, or m over the molecular weight, RT. So these are our ideal gas equations that we're going to use for this course. And when we want to calculate property changes of an ideal gas, we can do it simply by knowing Cp or Cv and molecular weight, of course. Have to know what substance it is to solve any particular problem. Now you'll find that these Cp's and Cv's are listed in any thermo book. You'll find them in your appendices. And one thing you'll notice is that Cp and Cv are a function of temperature. So you either need to get an approximation by taking an approximate average temperature for the process you're working on, or you'll need to integrate them. And in your text, and most thermotexts will give that function of T so that you can write delta U, for instance, is equal to the integral of Cv dt, where Cv is written out as a function of temperature. Often this Cv is given as a polynomial form as a function of temperature, fit empirically, meaning using the data, it's data fit to give Cv as a function of T. And then what you do to get delta U, the change in internal energy, is you integrate du. Now, one thing I should mention about the Cp and Cv values is that if you have, and this can be shown also, that Cp minus Cv is equal to R, the universal gas constant, Ru, divided by the molecular weight. If you were in molar units, which often in chemical engineering we'll use molar units, then you'd say Cp per mole minus Cv per mole would be equal to R. And that's convenient because often what you'll find listed are values of only Cp, and so you'll have to get Cv by subtracting R from it. So that's a handy little piece of information to have. Now let me move on to entropy changes of ideal gases. It can be shown that ds is equal to Cp over T dt minus R, I'll put Ru over molecular weight, dP over P. Or if we want to get, if we can take Cp to be approximately constant, we would say delta S over small ranges of temperature would be equal to Cp, because over small ranges of temperature, Cb will be approximately constant, would be Cp ln, when you integrate this term, ln of T2 over T1 minus Ru over molecular weight, ln of P2 over P1. And we'll use that later when we start doing processes involving entropy calculations for ideal gases. Now this is for an ideal gas again. For a real gas it gets a little more complicated. Now also another equation for finding ds we can use with Cv information is equal to Cv dt over T plus RU over molecular weight dV over V. So we'll get delta S for an ideal gas is equal to CV ln T2 over T1 plus R U over molecular weight ln of V2 over V1. And again, we'll use those calculations later on in the, as we start doing calculations with entropy. Okay, so to summarize, we have du for ideal gases is equal to CV dt. Or if the temperature change is small, we put small delta T, then we can assume that CV and CP are constants. So let's say du here is equal to CV dt delta U equals, for small delta T, let's just make this a category, delta U is equal to CV times delta T, which is T2 minus T1. dH is equal to CP dt delta H, again if we have small temperature changes, CP delta T. Delta S, let's say delta S for small temperature changes, again is CP ln of T2 over T1 minus R over molecular weight, RU over molecular weight, ln of P2 over P1, and delta S is equal to CV ln of T2 over T1 plus RU over molecular weight ln of V2 over V1. So there's 4 equations that are handy for solving for property changes, U, H, and S of ideal gases. Okay, now that we've talked about ideal gases, let's talk a little bit about equations for liquids, because it's nice to be able to find changes in internal energy or enthalpy for liquids, or entropy for that matter. Okay, now liquids are often thought of as incompressible, so we're going to make some approximations using that information. Also, liquids compared to gases have a very small V, a very small specific volume. V liquid is often much, much less than V of the gas. So that helps us out a bit too. Often what you'll see listed for liquids is heat capacity C sub P, but you won't often see CV liquid. So remember, Cp was equal to the change in H with respect to temperature at constant pressure. Typically you can get a pretty good pressure. Remember, pressure, liquids are primarily a function of temperature, so the pressure isn't going to make a big difference. So the volume changes can make a big difference. Of course, liquids aren't changing volume very much anyway. If we treat them as incompressible, the volume's not changing at all. So, with pressure. So we can take delta H over a small interval where Cp is constant to be equal to Cp delta T. Now we talked about how delta H is equal to delta U plus delta PV. And if we're looking at mainly a change in temperature and not a change in pressure, then the V, we we have the situation where V is very small, and so delta H for a liquid, particularly for changes in temperature, is approximately equal to delta U. So often for liquids we can use delta U is approximately equal to delta H, which is equal to Cp delta T. Now the exception of that is when we have as I mentioned earlier, when we have a pump, then we'll need to consider the delta PV term for the liquid, which is equal to P delta V plus V delta P. So onto the internal energy, we'd have to add the V delta P. Again, we're assuming delta V for a liquid is 0 because it's incompressible. I wanted you to be aware that if all that's happening is the temperature is changing of a liquid, then you can get a pretty good idea of the internal energy change to be the same as the enthalpy change, approximately. And you can use that, calculate that by using Cp delta T. Now it's a good idea to go into your tables and look and see what, and this is true for solids as well. Good idea to go to your tables in the back of your book, go to your appendices and just look at each page very carefully. You'll find a lot of things given for the heat capacity of liquids and solids, and you want to know you wanted to know how to go and find those CPs so you can solve problems with them. Get familiar with those tables in the back of your book because they're quite handy and you can find a lot of things there. So that pretty much summarizes. Now, last thing I should say is if you're calculating a change in energy with Cp delta T or Cv delta T, ideal gases or liquids, you need to make sure it stays in that phase. There's a large change in energy when a liquid turns into a vapor or a solid turns into a liquid or vice versa. So you can't ignore that. But if you know it's staying in the phase, you know it's staying as a gas, use Cp dt if it's an ideal gas. If it's a liquid, use Cp dt to get dH or delta H as long as you know it's staying a liquid. If it changes from liquid to vapor, then you have to add in that change of energy due to the phase change, and we'll talk about that a little bit later.